Okay, hey everybody, welcome back. So as we saw in our last video, we are now in the world where we want to study and talk about the derivative of a function. We have this formal definition, right, about measuring the derivative of a function, or saying that a function is differentiable at a point p if this limit, or equivalently this limit, exists. And if such a limit does exist, we'll denote it as f prime of p, right? So our function is differentiable at p if we can calculate its derivative f prime of p by computing these limits and getting an answer. We will often just simply say that a function is differentiable instead of saying it's differentiable at p. We'll often say it's differentiable if it's differentiable at every point in its domain. And so that is sort of in line with the language that we have developed in calculus and earlier math classes. So let's try to use this definition of differentiability and this limit idea to prove a fact that again, I think we've seen before and that we know. I should say a lot of the things that we'll be proving in the videos to come are things that we already know are true because we've seen them in Calc 1, but now we'll rigorously prove them with a real analyst's eye. And so what we're going to prove here is a theorem that essentially says, or a lemma, which essentially says if we have a function that is differentiable, then that function is also continuous, right? So every function that is differentiable at a point is automatically continuous at that same point. Okay, let's go ahead and try to rigorously prove this. So what we know is that our function is differentiable, right? We know f is differentiable, i.e., we know the limit as x goes to p of the quantity f of x minus f of p over x minus p exists, right? And in fact, it equals a number, which we are choosing to denote as f prime of p. So that limit is known to exist. What we want to show, right? We want to show, let's try that again. We want to show that the quantity, we want to show that f is continuous at p, right? F is continuous at p, i.e., that the limit as x goes to p of f of x is actually equal to f of p. This was our definition of continuity from back in chapter 7. So that is what we explicitly want to show. Now, you might think that we would have to construct some sort of challenging epsilon delta argument here, right? We're dealing with these, we know that some limit is true, which means that we know that there's some epsilon delta structure that is true. We're trying to show that this limit equals f of p. Therefore, we're trying to show that some epsilon delta structure holds true down here. And so you might start by trying to think in terms of epsilons and deltas. Now, you wouldn't be wrong in doing that, but there are some sort of clever strategies we can use here to avoid doing that. In other words, we've already done a lot of excellent groundwork back in chapter 7 that had to do with, that had to do with limits of functions and specifically the algebra of functions. And so let's try to remember a given fact. I want to look up exactly what number this is. Okay, and so it turns out what we really want here is theorem 6.9. So it should be chapter 6, not chapter 7. But in chapter 6, we looked at functions and function limits. And theorem 6.9 discussed the algebra of limits. This was the one that said that if you had sort of two functions, you wanted to take a limit of, say, f times g, then the limit of the function f times g was equal to the limit of the function f times the limit of the function g, assuming that both f and g themselves were functions that had appropriate limits. Now, we can apply this not to an f and a g, but to this quantity right here, and an appropriate second quantity, which will be, it turns out, x minus p. So let's go ahead and set this up. We know, right? We know, and I'm just going to be writing exactly what we have up top. We know that the limit as x goes to p of the quantity f of x minus f of p over x minus p, we know that that quantity exists and it equals a number that's f prime of p. We know that because our function is differentiable. At the same time, we also know that the limit as x goes to p of the quantity x minus p, right? Well, x minus p, that's a linear function. That's a first order polynomial. We have seen that those are continuous. And in fact, this goes to p minus p, which is just equal to 0. So those are two limits that we definitely know. And our strategy is going to be to take this limit and take this limit, and then calculate the limit that we would get by multiplying this quantity times this quantity. And so we can do that in the very next line. So we get that the limit as x goes to p of the quantity f of x minus f of p over x minus p, right? That's the first bit, times the quantity x minus p. Well, by the algebra of limits, the limit of this thing times this thing will equal the limit of the first piece times the limit of the second piece. So this should just become f prime of p times 0, which is equal to 0, right? And so therefore, that's going to tell us that the limit as x goes to p, and now we can do some algebra inside the parentheses here, right? That x minus p can cancel with that x minus p. So we get the limit as x goes to p of f of x minus f of p is equal to 0. And because f of p is just a constant, right? The same algebra rules involving limits will allow me to add plus f of p to each side here. So plus f of p plus f of p. And so what we get in the end is that the limit as x goes to p of f of x is actually equal to f of p, which is exactly what we were trying to show. So, hooray. Awesome. So here you get a taste of how you can use our previous work, our chapter 6 work on functions and limits of functions to draw conclusions about derivatives. And we'll see more of that in the next video. So thanks so much for watching. I'll see you next time.